Okay, let's get started. This hour, our speaker is Tim Lantzsch from the Fraunhofer Institute of Laser Technology, the ILT, in Aachen, Germany. And Tim is a group leader for the powder bed fusion team at the Fraunhofer ILT for systems engineering and processes. And he'll be, I should also mention that he is a PhD candidate at the RWTH at Aachen University. And his area of research is in the optical systems and processes for hyper-accelerated productivity. So, Tim, thanks very much for joining us. Looking forward to your talk.
So, hello? Yeah, now it works. Thanks, Rob, for the nice introduction. I'm very glad that you all joined my talk today on the potentials of ring intensity distributions for laser powder bed fusion, mainly of nickel-based alloys, but in principle for all common AM materials. So I want to start things off by giving you a brief introduction to the topic. Then we'll follow with some of the results we obtained over the last approximately 1.5 years. We did the research with Enlight and also with Optoprim. And then we'll give you a brief summary of our work and also some outlook topics for the future. So, as some of you may know, we are researching L-PBF in Aachen for a very long time already, more than 25 years now. The basic patent was actually filed in 1996, so exactly 25 years ago, and we have just released also a video on that. So if you haven't seen it, just check our social media channels. It's very interesting if you want to see a bit of L-PBF history already. But we didn't get stuck 25 years ago. We worked a lot on the technology, and we are really now trying to pushing the boundaries, what can be done by L-PBF and by AM in general, by also developing the next generation of L-PBF systems, which also includes new laser beam sources that allow much more productive and efficient processing, basically. So nowadays there are two main approaches when it comes to scaling of productivity of L-PBF machines. So on the one hand side, you can just multiply the number of laser scanner systems, so the number of scanners and the number of lasers, to have them working in parallel and reducing the build time by just splitting the workload between the different scanning units. However, this is of course a bit costly because every laser and every scanner brings its own cost into the machine. A different approach that has already been existing also for a couple of years is using higher laser powers. However, this is in a way limited because of several factors such as byproduct formation and this kind of stuff. And of course, in the future, also combinations of both are thinkable. So combining high power lasers with multi-laser systems to have really highly productive machines. But for this talk, I want to focus on the high power side of things. So the build-up rate, at least the theoretical build-up rate in L-PBF is mainly defined via the processing parameters, namely the scan speed, the layer thickness, and the hatching distance. So in principle, to scale up the productivity, you need to enhance these three parameters to get as productive as possible. However, of course, there's a physical limit to that. You need to have sufficient energy input to fully melt the material and have no lack of fusion between layers and between several scan tracks. And on the other side, there's also an upper limit, because at some point in time when your laser intensity just gets too high, you will just evaporate material and will cause a lot of part defects. And that can be seen on this slide here. So when you consider Gaussian intensity distribution, single mode, at a fixed beam diameter, and you scale the laser power, your maximum intensity in the center will just peak, and at some point in time, the intensity will be so high that you evaporate the material instead of just melting it, which causes a lot of spatter, as you can see in the picture. And these byproducts then can interact with the laser beam to cause phenomena such as absorption or scattering of the laser radiation, which reduces the effective energy input, or also defects that stem from the byproducts itself, because they, in a way, land on the powder bed and in some regions can cause lack of fusion defects. So, now for the investigations we did, we used two different configurations with the AFX lasers. So in the very beginning, we were really lucky to get one of the first prototypes that could only deliver a ring beam, and we combined it with a 2D scanning system, meaning a galvo scanner and an f-theta lens, to research the general feasibility. And then as soon as the real product got available, we got a hand of it and combined it with one of our 3D scanning systems, so dynamic focusing unit plus galvo scanner, which then is more to the most of the common L-PBF machines that are out there in the market. And there we then varied the laser beam profile via switching the AFX indexes. So at first, as I mentioned, we started with a 2D system, and to investigate how the melt pool behaves and how it forms when you use a ring-shaped intensity distribution compared to single-mode Gaussian. We did some kind of standard scan pattern consisting of several scan lines and also interconnected single layers. We varied the laser power and the scanning speed, and we compared the laser pointer is probably not showing on the screen, but we compared the 80 microns Gaussian and 100 microns Gaussian, which is considered state-of-the-art in most machines. Most machines work with 80 to 100 microns Gaussian intensity distribution. And we also took Gaussian defocused to 160 microns as a reference to see which impact the intensity profile itself has while having a similar beam diameter. So now on this slide you can see some results for these intensity profiles for same processing parameters but different intensity distribution and beam diameter. And you can see clearly that for the smaller beam diameters Gaussian, you have a more keyhole dominated process, so very deep and narrow melt pool with a risk of keyhole pore formation, and also the difference is very apparent. So for the small laser spot sizes, Gaussian intensity distribution, very strong keyhole formation. And for the larger beam diameters, ring mode and Gaussian, you have a more heat conduction dominated processing regime, flatter melt pool, wider melt pool. But when you compare the Gaussian and the ring mode side by side, you will realize that the tendency is that the ring mode profile yields a wider melt pool, which could be beneficial in terms of processing speed. What we then did was more detailed comparison of the both by varying all the scan speed and the laser power, and we analyzed depending on the line energy, which is basically just the ratio of laser power and scan speed, how the melt pool behaves. And the interesting finding is that for the state-of-the-art, let's call it state-of-the-art Gaussian intensity distributions, you will at some point have a transition from a more heat conduction dominated processing regime to a keyhole dominated processing regime. And this transition occurs at approximately 0.2 to 0.4 joules per millimeter. Whereas for the defocused Gaussian and also for the ring mode, you don't have this transition. You always stick in this heat conduction dominated processing regime and do not have the risk of keyhole formation. And if you then compare the defocused and the ring mode side by side, you will also see that for the melt pool width, the ring mode is generally larger, independent of the processing parameters, which kind of makes sense because the intensity with the beam profile is more towards the sides of the laser beam instead of in the center. Additionally, we tried to do some first test cubes with the prototype to see if it also works in the process. We varied all the processing parameters and identified suitable process parameter combinations that yield density above 99.5% while maximizing the productivity. And we found 3 parameter sets that we compared, which is on the one hand side reference, so parameters very close to the ones you use for single mode Gaussian laser beams. Then max scan speed, which means maximizing scan speed while keeping a layer thickness of 50 microns. And then we also tried to maximize productivity, so also scaling layer thickness to even get a higher productivity. And when you then analyze the results, you see density works for all of them, so 99.5% is not a problem. You see some stronger scattering with regard to the relative density when you look at the max productivity, because, yeah, of course, it makes kind of sense that when the melt pool is more shallow and wide, it is more difficult to really melt high layer thicknesses, but the max scan speed works really well. So compared to standard processing parameters, we have a scaling of approximately factor of 2 just via the scan speed compared to our reference. And that was our starting point to then look into the final product itself. And in this video you see the process, and of course it appears to have a lot of spatter, but you have to keep in mind that you melt twice the volume basically in the same amount of time, so per volume the spattering isn't even that bad. Additionally, we investigated contour accuracy and surface roughness. Here we found that in general the ring yields a slightly higher surface roughness than single mode Gaussian, which also makes kind of sense. The melt pool is wider, and therefore you probably have a lot more powder particles being stuck to the part, which then was our motivation to say, okay, adapted processing strategies with ring and single mode make a lot of sense, because you have the high productivity for the edge of the part and can then have also the high surface quality for the Gaussian during contour exposure. Which now brings us to the results that we obtained with the final AFX product. So as I mentioned, we coupled it with one of our 3D scanning systems, as it is in most L-PBF machines. We measured the system to see if it yields the properties that we calculated, so caustic and laser characteristics measurement for index 0, 3, and 6. And we found that the resulting beam diameters corresponded very well to our calculations, and we found also that the focal planes actually align very well. Also here, not yet. We did the process parameter development for Inconel 625. Also criteria here was above 99.5% for the relative density, but instead of comparing scan speed and layer thickness or productivity as a whole, we compared the AFX indexes 0, 3, and 6, which correspond to 100% single mode Gaussian, 50-50 between single mode and ring mode, and almost 100% ring mode. And through the data you see in this upper graph, and also through the cut sections below, you see the density isn't really an issue. Processing up to 99.5, even 99.9% density is possible with all settings. However, the AFX index 6 allows us a scaling of the productivity by a factor of 2.5 compared to the single mode Gaussian, which is really quite impressive, because through just switching the intensity profile, we suddenly have the tool to really have high productivity L-PBF processes, and we still have the flexibility that comes with the single mode Gaussian beam. I also included some videos, and also here you see the AFX index 6 process, and I will skip back and play it again if it works. It's just way faster. So in the time one of these test cubes is exposed in the left video, already 3 cubes are processed in the right-hand video on the right-hand side. And we also did some OT process monitoring during the builds, and we found that there were no major deviations, so no cold or hot spots in the process. You see that the part contour is a bit overexposed in these images, but this is just due to the fact that the process emission at these higher laser powers is generally stronger. Yeah, and this already brings us to my summary and outlook. So, as I mentioned, we were able to find very productive processing parameters for Inconel 625, which allowed us to scale the productivity by a factor of 2.5 compared to our reference, which is single mode Gaussian. The processing regime over the entire process parameter range was found to be heat conduction dominated, no keyhole formation, no risk of keyhole formation whatsoever. The melt pools are nice and flat, rather wide compared to our Gaussian reference, even when considering the defocused Gaussian. Nevertheless, there are also some constraints when it comes to layer thickness. It is difficult just with this heat conduction based process to really scale the productivity. You have rather to scale via the hatching distance and the scan speed, and also contour when just processing with the ring mode beam is slightly rougher than for the Gaussian reference, which can be solved by combined adaptive processing with the switchable AFX laser beam source. Nevertheless, there are still a lot of open points we want to address in the future. So first of all, we demonstrated that it works for Inconel 625 with high density. However, to ensure appropriate application properties, we of course need to get additional data regarding microstructure and also mechanical properties of the part. That's what we're currently investigating. Furthermore, I already mentioned the additional degree of freedom we get basically from the laser beam source while having the opportunity to switch between beam profiles gives us a lot of leeway to have adaptive process control for highly productive but also high complexity and high quality L-PBF parts. And then, of course, we have some more insight into the, as I mentioned, the melt pool is flatter, the energy input at the same energy input as for the Gaussian, which also is very interesting for processing of hard-to-weld materials because we can control microstructure evolution and also heat-affected zones, which may be beneficial for the future for these very critical materials and new material development. And one last thing, which is also a very important topic for us, I mentioned that we are working on next generation machines. You may have seen our big prototype, and of course a dream for the future would be to have really large machines and really productive machines. And this could also be an aspect where the AFX could fit well to combine what we already have in terms of build size, the processes we have established, and further enhance it with the tools that the AFX laser can provide us. So that's it from my side. Thank you for the attention, and feel free to ask if you have any questions.
So we're going to try to make Tim talk a little bit more. If anyone has some questions, please ask. Yeah.
So the colleague here was asking if we also tried other settings and if we have also considered other settings, and that's true. We have stuck to the 3 settings here, which was our starting point. in the beginning we figured it was a good idea to have the almost 100% on both sides and the 50-50 in terms of power. We realized that because the ring is bigger, the 50-50 doesn't really make sense, because it's basically the high intensity peak in the middle that defines the process. So what could be really interesting would be to go more into the direction of having 50-50 ratio in terms of intensity compared to the power ratio, and that would be probably more towards index 4, 5, something in this range. Okay, you were asking if we've also considered using this scalability approach or the broader processing window to transfer parameters or make transfer of parameters from one machine to another easier. So we haven't done this, but I know that a lot of colleagues have been here and have also given their presentations on various topics. So I think that could definitely be a point for the future to see if this can help, or the generally broader processing parameter range makes it easier to transfer the parameters, yes. Yeah, that's actually also a very interesting research topic for us, not only for different beam shapes, but also just in general, the processing with temporal modulation, meaning pulsing, but temporal, you could also thinking about wobbling or something like that. I think it could be beneficial if you want to really fine-tune, for example, microstructure. If you combine then what you know from pulse modulated processing, that you have some kind of discrete solidification with smaller independent melt pools, together with the fact that the melt pool that results will probably be rather shallow and wide, this could also be an additional degree of freedom you could use to fine-tune your part microstructure, for example. Yeah, thank you for inviting me, and it was a pleasure.